Hello students, in our DME class, we were discussing about design of couplings. In today's class, we will discuss the design of bush pin type flexible coupling. First of all, guys, this is a flexible coupling. Flexible coupling means in this coupling, there is some misalignment which is allowed. Actually, the flange coupling, muff coupling, split muff coupling were all rigid couplings because in those couplings the misalignment of the shafts were not allowed. In this case, you will see in the diagram that we will use rubber bush. Due to the rubber bush, there is some misalignment of the shafts which is allowed. So a bush pin type flexible coupling is a modification of rigid type of flange coupling. So as we have discussed in the previous classes about rigid coupling, that is flange coupling, this coupling is the modification of the rigid flange coupling. The coupling bolts are known as pins. In this case, the bolts that we use in the flange coupling are known as pins. The rubber or leather bushes were used over the pins. So to provide the flexibility in the coupling, we will use rubber or leather bushes. The two halves of the coupling are dissimilar in construction. The clearance of 5 mm is left between the face of two halves of the coupling. This thing you will see in the diagram. There is no rigid connection between them and drive takes place through the medium of compressible rubber or leather bushes. So this is the diagram for bush pin type flexible coupling. You will see there is a gap of this gap 5 mm between the faces of two flanges, and we will use the shaft which is of diameter D. This is same hub that we will use in the flange coupling. Hub, the dia of the hub is 2D, that is capital D. This is flange, outside dia of the flange is D2. This is your pitch circle dia D1, and the length of the hub is same, that is 1.5D. The thickness of the flange we take it as small l. Now in this case, this is the important thing. Instead of using bolts, we were using pins here. So the pin that we use in the bush type flexible coupling is this type of pin. In this pin, one of the portion, that is left portion, have diameter large, and on the right side we have small dia. This dia on the right side, which have threads, is taken as D1. The diameter on the left side is covered with brass. This is black portion is brass bush, and brass bush have a thickness of 2 mm. This blue shade, this is rubber bush, and it is have a thickness of 6 mm. The head, cheese head of the bolt is taken as D2. So in this coupling, we will design the similar things, that is shaft design, hub design, this flange design, key design. But the difference of this coupling from the previous coupling would be the design of the pin that we use instead of bolts to provide the flexibility in the coupling. So let's start the question. So this is your question. Design a bush pin type flexible coupling to connect a pump shaft to a motor shaft transmitting 32 kilowatt. This is power at 960 rpm. This is rpm. So from power and rpm, you will always find torque. The overall torque is 20% more than the mean torque. So this is your maximum torque. You will multiply the mean torque by 1.2 to increase it to 20%. The material properties are as follows. The allowable shear and crushing stress for the shaft and key material is 40 megapascal and 80 megapascal. So this is your shear stress 40 megapascal and this 80 megapascal is your crushing stress. These are the stresses for key material and shaft material. The allowable shear stress for the cast iron is 15 megapascal. Allowable bearing pressure for rubber bush is 0.8 Newton per mm square. The material of the pin is same as that of shaft and key. Minimum dia of the pin is 20 mm. Number of pins is equal to 6. This datum you have to assume. Sometimes it is given, sometimes you have to assume. Draw neat sketch of the coupling. So this is your statement. So first of all, we will write the given data, that is power is 32 kilowatt. We will write it as 32 into 10 to the power 3 watt. RPM is 960. Maximum torque is 1.2 times the mean torque. Shear stress for the shaft and key is 40. Crushing stress for the shaft and key is 80. And shear stress for the cast iron is 15 megapascal. Bearing pressure is 0.8. The bush pin type flexible coupling is designed as discussed below. So in the first step, we will design the pin. The pin which we use instead of bolts, the pin is covered with rubber bush. So we will design the pin. First of all, we have to find the diameter of the shaft. How will you find the diameter? First of all, calculate torque from the same formula. This is 318.3. Now find maximum torque, which is 20% more than the mean torque, and it is 382 into 10 raised power 3. Now equate this torque with pi by 16 into tau d cube, and from this relation, just put the value of shear stress, and you will get the diameter of the shaft as 36.5, or we can standardize it as 40. So number of pins, we will take it as 6. So this is the formula for diameter of the pins. This D1, small d1 is the diameter of the pin. It is calculated as 0.5 d upon n under root, where d is the diameter of the shaft, n is the number of pins. So put the value of d and n and you will get the diameter of the pins 8.2. The length of the pin of least diameter, that is D1, is equal to 20 mm, is threaded and skewed in the right hand coupling half by standard nut and washer. So this diameter, which is 8.2, has now been standardized by 20 mm because this D1 is very small, 8 mm is very small, and it will not be able to bear the stresses due to bending and shearing. So we will take this D1 as 20 mm. The large portion of the pin which is on the left hand coupling half is made 24 mm diameter. So we will take it as this D1 as 20 and this D as 24. On the enlarged portion, a brass bush of thickness 2 mm is pressed. So this is your black portion is brass bush whose thickness is 2 mm, and a brass bush carries a rubber bush. Rubber bush has a thickness of 6 mm. So overall diameter becomes 24 plus this is 24, 24 plus 2 and 2 that is 4, 6 and 6 that is 12. So 24 plus 2 and 2 4, 2 into 6 12. The overall diameter becomes 40 mm. So this is your D2. We have found the diameter on the left side D2 and on the right side D1 which is 20 and D2 is 40. So rest of the question we will do in the next part. Thank you guys.